do them, yeah. And the mic works, okay. Okay, welcome everyone to the last talk in the session. With a rather cryptic title, I'm going to explain what those means, but I want to talk about how we can build arguments from kPRISIS. I'm Christian, I'm from EPFL, and this is joint work with Jonathan Boodle from IBM Research in Zurich and Zi Guan from EPFL. They're both also here at the workshop. So we're here because we care about arguments, and a typical way to build arguments is to combine two building blocks, an interactive oracle proof, an IOP, and a commitment scheme. And in full generality, the IOP can be functional, meaning that the prover sends proof strings, and the verifier can have oracle access to these proof strings in the form of functional queries. So for example, it can do inner products of its query with the proof string, or polynomial evaluations, or many more things. And correspondingly, the commitment itself is also functional. So you can commit to a long proof string as a short commitment, and then the prover can give an opening proof that the commitment, when kind of evaluated at the query, gives the opening y and commits the verifier of that. So these are the building blocks that we need. I want to focus on the crypto part of the commitment itself. We have many functional commitments, both pre-quantum, bulletproof, story, KZG, and post-quantum, Greyhound, lattice bulletproofs, new approaches based on some check, many, many more. Interestingly, we can split those into two groups, specifically by whether they have kind of very few rounds, ideally kind of if they're non-interactive, or if they have more rounds. Say, for example, they have logarithmically many rounds, if you have kind of some check or some folding happening. And having very few rounds, or even being non-interactive, has a lot of advantages. Typically, this leads to very short proofs. It's more recursion friendly because you don't have to do Fiat-Shamir as often. And conceptually, in theory, it's also very nice to see how far you can go, removing interactivity from your crypto thing and shifting everything to the kind of information theoretic part of your protocol. And you'll notice that the bottom right quadrant is suspiciously empty. So in this work, we wanted to explore and see if there exists non-interactive lattice-based functional commitments that we can actually use to build arguments. And I'll explain a bit why this is non-trivial and why it's not immediately clear that these things exist. So that's the plan. So our high-level goal is to apply this kind of generic theorem that says if you have a knowledge-sound FIOP, in this case we'll focus on the linear IOP because we want to work with lattices, and lattices are basically linear algebra. So linear queries are very natural classes of queries to support. And you also add a function-binding linear commitment. Function binding here is some security notion that is sufficient. You will get a knowledge-sound argument. So that's the master theorem that we want to use. So in particular, we'll need to provide a linear IOP for NP and a non-interactive, in this case, we want to go to the extreme, function-binding linear commitment under some falsifiable lattice assumption. Specifically, as you might have guessed from the title, we want to go for kPRISIS. So this is K, polynomial, ring, inhomogeneous, short integer solution. It's a SIS with hints assumptions, so short integer solutions, but the prover additionally gets some hints, some preimages. You can think of it, if you come from the pairing world, as a lattice equivalent of a Diffie-Hellman type assumption. Now, we can't really build non-interactive function-binding linear commitments from lattices. This doesn't quite work. Instead, we have to settle for something weaker, namely a new notion that we introduced called coordinate-wise function binding. So coordinate-wise function binding sits between evaluation binding and function binding, and it's much weaker than extractability. So that's what we will have to settle for. Of course, we also need to adapt the other building blocks. So we'll need the IOP to also support these kind of coordinate-wise queries. And then we also need to strengthen the theorem to still work even if we start from a weaker linear commitment to still, in the end, achieve a sound argument. We also have kind of a further step. Instead of showing coordinate-wise function binding directly, it will actually show a rather weak property on the commitment scheme. So simply evaluation binding, which says that if I give you a query and two conflicting answers, then I should be able to convince you that the same query opens to two different things on the committed vector. And then generically, for any linear commitment that is both somewhat homomorphic and evaluation binding, you can actually recover a coordinate-wise function binding property. And that's enough for our framework to work. And finally, as some goodie, because we also want to have sublinear verifier time, we also focus on the holographic setting for the linear IOP, and we also boost the theorem further to handle holography and give you a pre-processing argument. So that's the roadmap. I want to talk mainly about the commitment scheme itself and this kind of generic lemma. Any questions so far? Okay, so I'm going to give you a pairing-like lattice-based linear commitment scheme. So a linear commitment scheme has four algorithms. We do generation of parameters for a given vector length L. We commit to a vector x of length L using these public parameters. Here the vector is going to be small, so the entries are kind of a bounded norm, and we'll get a commitment. We'll have an opening algorithm that takes public parameters, commitments, a query. The query is also going to be short, a purported evaluation y and the vector, and it's going to give us a proof. So this is non-interactive, and a corresponding check algorithm that also takes public parameters, commitment, query, opening, a proof, and decides whether it accepts or rejects this. The scheme I'm going to present is actually a simplification optimizations of the Orb-Weaver commitment scheme in FLV23, which itself is an optimization of the ACLMT22 commitment, which itself is kind of a lattice equivalent of pairing-based constructions that were kind of pre-existing before KZG, for some historical context. So to do generation, we're going to sample some ring element V. So we work over some polynomial ring RQ. V needs to be invertible. That's why it's from RQ star. And then we're going to use pre-image sampling to sample some short vectors UI with the property that for the public vector A, when we do the inner product of A and UI, we get powers of V, both negative and positive powers of V. And then the public parameters are just going to be A and V and a bunch of pre-images. And so we'll send U minus L minus 1, all the way to U minus 1, and then U1, and then U all the way to L minus 1. We won't send a pre-image of V to the 0 of the unit. So that's going to be kind of excluded, but you'll see everything else as a prover. To commit, we'll just take a linear combination of the entries of X with powers of V. And for opening, we'll consider the following formal polynomial. So it's a Laurent polynomial, so it has both negative and positive powers. And it has this specific factorization. The first part on the left encodes X with positive powers of X, and the second part encodes the query Q with negative powers of the variable X. And if you multiply everything out, you'll see that the constant term here is going to be the inner product of the query and the vector. So it's exactly the y that we actually want to open to, plus a bunch of cross terms. And in the proof, we'll kind of commit to the cross terms using the short pre-images that we have in the public parameters. So we'll send a linear combination of the yi ui for all the yi's except y0, which encodes the opening. And then for the check, we'll check some norms, as is usual. So the proof and the opening both have to have bounded norm. And then we'll check the following linear query. It's not too important what it is, but it's pretty simple. You'll check that PF is actually a pre-image under this linear map defined by A. And when you add Y to S, you should recover CM times QJ V1J. Roughly why we do this is, you can work out completeness. In yellow, I show things related to the commitment. In green, things related to the query. In blue, things related to the cross terms. And in pink, the things related to the opening. And you can see, if you have both colors on the 4 colors on the left and 4 colors on the right, roughly things match up. And so if this is actually the opening, then the check is going to pass. So that's the commitment scheme. Any question on the definition itself? Okay, then I want to convince you that this commitment scheme is evaluation binding under the following lattice assumption. So this kPRISIS. This assumption says that it's hard to find a short vector U star and a short kind of slack factor S star, which is non-zero, such that U is a pre-image of S under this map A, even if you've seen the public parameters, which include a bunch of pre-images for unrelated targets. So in particular, S star here does not depend on V. This is really kind of, we're actually trying to get the adversary to find a pre-image for the unit 1, and we're allowing it some fudge factor S star to maybe do some magic during the reduction. And then the proof of evaluation binding is actually quite easy. So assume that you're given a single query, 2 conflicting openings, and 2 proofs for these openings. You can actually subtract the verification equations, and you get that A inner product with proof minus proof star actually will map to y prime minus y. And so you directly have your U star and S star for the kPRISIS solution. So that's kind of a rather elementary proof. So we're kind of on the left with evaluation binding. Unfortunately, that's in general not enough to give you secure arguments. So in general, what we know is that function binding at least suffices. It's unclear if it's necessary, but we have reason to believe that it is necessary in general. And you can have stronger properties all the way to extractability, but these are even harder to achieve. So with kPRISIS, we are here for this commitment scheme. We can look at a slightly different schemes, the ones that were introduced in earlier work, where you can additionally add some commitments, and then under a knowledge assumption, you can actually show that it's extractable by just looking at the commitment and assuming that you can magically recover what was committed using the knowledge property of the assumption. Now, knowledge assumptions in lattices are usually pretty tricky, and at least this one was kind of morally broken by Wee and Wu, so we have reason to believe that this is not really something that we can do to show security. So the question is, okay, can we actually build arguments from this? It's a nice linear commitment scheme. It's not trivially broken. Is it strong enough to build arguments? Unclear. And actually, this is a common pattern in these kind of non-interactive commitment schemes from lattices. If you want to open to linear functions or polynomials or functions in general, it's very easy to show evaluation binding. And we don't really know how to go further than that for function binding, say, let even extractability. So we're going to, this explains also the title. So we want to kind of come back from this knowledge crisis, which was a pun by the paper that introduced the assumption, and show that the falsifiable kPRISIS assumption is actually enough. And we're going to do this by relaxing the property that we want to achieve. So we're going to go from function binding to coordinate-wise function binding. So I'll sketch the reduction. Suppose you're giving a commitment and then a bunch of queries, openings, and proofs, say from 0 to L. And these satisfy two conditions. So first, all the proofs are accepting. And second, they define kind of a system of equation that is not satisfiable. So for every purported vector x that you can give me, there's going to be at least one index for these queries and openings that is going to be inconsistent with this vector. And then we want to have an evaluation binding output. So we want to have a commitment, a single query, two openings and two proofs, so that the proofs verify and the openings are distinct. And for this, we're going to require something on top of our queries. So we also require that the queries have a specific form. Namely, they're going to have this coordinate-wise predicate applied to them. And this means that there is kind of a central vector, Q0, and then all the vectors after that, Q1 to QL, are going to differ from Q0 in exactly one index, namely the ith index. So if you subtract Qi and Q0, you'll get delta I times the indicator vector for the ith entry. And furthermore, this kind of delta I, this difference between these two queries, is going to be invertible in the ring. And it's also its inverse is also going to have low norm. So we can leverage this property to kind of solve more efficiently for preimages. That's the first that we need. The second one is we need some kind of limited homomorphism of the scheme. Here I'm just writing homomorphism everywhere. This is lattices, so it's going to be somewhat homomorphic under suitable norm bounds, but I'm going to ignore those for the purposes of this talk. So roughly how we'll do this, we'll compute these quantities here. So we'll always subtract the ith entry and the 0th entry, and then we're going to multiply by the inverse of delta I, which is this difference between these two queries. So for the query, we'll get delta I inverse Qi minus Q0, and that's going to be the indicator vector by the coordinate-wise predicate. Then we can do the same for the openings, and that's going to give you some quantity that we can call xi, and then some proof. And by homomorphism, because kind of all the query answer proofs were accepting, the linear combination is also going to be accepting under suitable norm bounds. And what this is saying really is that you have a valid proof to open the indicator vector at xi. So you know that there should be a vector whose ith entry is exactly xi. And so using this, we can set x to be this purported vector that we want to attack. Then we can find some index in all of these queries that we have so that the query and the answer disagree for this vector. And then we can use homomorphism again to compute a conflicting opening for the same query. So we'll kind of compute the query Q here by just kind of combining these indicator vectors with the coefficients. we'll get a different opening y prime, which is different from, by assumption, and then some other proof that is also going to be somewhat short. And that's going to be exactly what we need for evaluation binding. And so here, I've only really used the fact that these queries kind of have this special structure, and I'm assuming that, like, when we compile this into an argument, there's like some reminder from higher up that can give us this structure, and the homomorphism. These are the two things that we need, and that's enough. Okay, so that's kind of to conclude on the more kind of crypto side. So we can actually, we know nice evaluation binding linear commitment schemes from lattice assumptions, and generically we can lift them to coordinate-wise function binding. Now you might ask, okay, sure, you have this property. Like, can you even compile this with? Like, is there an IOP that you can actually compile this with? In fact, we give a positive answer to that as well. And the linear IOP that I'm going to show you is actually compatible with this paradigm. It's actually very natural. So actually, we start from the Labrador argument, which you might kind of know it's a very seminal argument by now, has been used many times, has extremely short proofs, but that's not what we care about today. Internally, this is a series of reductions, kind of log many reductions that take an input and compress it. And actually, if you squinted it enough, you can decompile this into a linear IOP and a linear commitment scheme. So the one that Labrador uses is kind of a double itie commitment, where you do itie twice, and then you just send the openings as the proof. So it's kind of a trivial commitment scheme with a bit more compression. And we actually write down the Labrador LIOP that you can extract from this. It's a 3-round LIOP. For a witness that has this specific size, so R and N are like 2 parameters that you can pick. We also kind of would like this to be succinct in the verification. So the Labrador LIOP is going to be succinct when you compile it with a compressing commitment. Ideally, we want the verifier to be succinct as well. This is not the case in Labrador. As you know, Labrador has a linear time verifier. So the first thing that we do is that we rebalance the randomness complexity of the verifier across rounds. So in the first round, the Labrador verifier will have to send projections that are going to be kind of security parameter, time, length of the witness. And then later on, there's going to be a check that is going to be kind of lambda squared challenges. And obviously, if the verifier has to sample something that is length of the witness, then it's going to be linear in the witness size. So what we can do instead is we can send fewer projections, let's say kind of only one of size n, and then do some repetition. And then we pay for this later on, where we have to do more checks, namely kind of r times more checks. But because these are two balanced, you can pick r and n such that actually the verifier is sublinear. So that's what we do. And then you can also make the linear commitment scheme be succinct in the check for structured queries. So in general, you've seen before, like the linear commitment check has to compute, basically has to touch every bit in the entry. But it turns out that the queries that the Labrador LIOP uses are very structured, and so you can actually get away with either r or n kind of many entries instead of r times n. The second issue with the Labrador IOP or the instance that it targets is that the instance itself has size that is larger than the witness size. So for the verifier, it will have to read at least the witness size anyway. And so to get away around this issue, we use the standard trick of holography. So we split the index into the instance into a big index and a very slim index, so that there's an indexer algorithm that processes the index and gives this out as an oracle string that the approver will have access to, the verifier will have access to later on. And then the instance is actually just a constant amount of bits that the verifier will have to read. And in the end, I'm not going to go into the details, but you can show that actually the queries that the Labrador construction uses actually satisfy this coordinate-wise predicate. So it's also possible there's many other constructions out there that use the same kind of trick that are that you can directly instantiate with this commitment scheme or any other commitment scheme that also satisfies coordinate-wise function binding. So that was what I showed. There are nice non-interactive lattice-based commitment schemes that you can use to actually build secure arguments. There is a nice linear IOP. I want to just highlight a few things. this kind of line of research was kind of abandoned because knowledge crisis was broken and nobody knew really how to use these things to build arguments, and so we were kind of at the limit in terms of how crazy the falsifiable assumptions can get. And actually, this shows that this line of research of kind of porting pairing-based constructions to lattices is actually still useful for the purpose of building arguments, and so that would be very interesting to kind of try and make them concretely efficient, for example. And on the other hand, I don't know how many lattice people we have here, but you can actually squint at those lattice arguments, which are not always nicely written down, and actually extract a very nice information theory core. And maybe this is also something that we should do a bit more as a community to try and separate things and make them more modular so that you can reuse the same constructions with different commitment schemes, once a new commitment scheme comes out, and you can directly get a new argument without having to, decompile and recompile the same construction over and over again. That's it for me, and I'm happy to take questions.
Any questions?
So very nice talk. I actually have like 15 questions, but maybe I can catch you later for, for more discussion. But just now, for now, this notion that you introduce, which is coordinate-wise function binding, sounds a lot to me like of having a somewhere extractability kind of flavor. Have you thought about this?
Sorry,
somewhere extractability? Are you familiar with, or
have
you thought about if this relates in some way?
I'm not sure it does. I think the coordinate-wise specifically is more a trick to, instead of doing like solving a linear system equations, to make a structured linear system so that you can extract things. And it's, I think, closer to like the coordinate-wise special soundness for Sigma protocols. I don't immediately see a link with somewhere extractability, but maybe there is. I don't know.
Okay.
Yeah.
Any other questions? Besides the 15 different questions. Okay, then let's thank Christian again.